Um, I will try to reiterate a little bit about what we discussed last time, and also add more details on it. The central motion, the central force motion. We start with an isolated system consisting of two particles interacting under a conservative force, conservative central force. In other words, it is the force is directed between two particles, m1 and m2, and the position vectors are r1 vector and r2 vector. All right, and r vector is the difference between these two position vectors. Now the equation of motion are given by equation 2 and equation 3. For equation 2, we have for particle 1, we have m1 r1 double dot equal to fr r hat. In other words, it's pointing in this direction, right? And for particle 2, we have the Newton's equation of motion, m2 r2 double dot equal to minus fr r hat. This is due to the action in reaction pairs, right? The force is attractive if fr is less than 0, and it is repulsive for fr greater than 0. Now, equation 2 and equation 3 are coupled together by the vector r. The behavior of r1 and r2 depends on the difference of the two position vectors. Okay. Now let us go to the center of mass frame. Let us make a change of variables. We generate the center of mass position vector, R vector, capital R vector, and also the relative coordinate position vector, that is the small r vector. All right. Now the equation of motion for the center of mass position vector is given here. If we differentiate the center of mass coordinate twice, then we get, as shown in equation 6, we get 0, which implies that the simple solution is the acceptable solution. R vector equal to the constant vector plus vt. All right, because the acceleration is 0, and the center of mass particle moves with a uniform velocity. Now, if we choose the center of mass frame as our reference frame, then the velocity will be 0. And the r not equal to 0. In other words, the origin, we just pick the origin equal to 0 as the center mass frame, all right, in the center mass frame. So the whole thing remains as 0. The capital R vector remains as 0 for all time. On the other hand, the equation of motion for the relative coordinate can be obtained as follows. We differentiate the R vector twice. Then we have two terms. The first term is R1 double dot. The second term is R2 double dot. R1 double dot gives you F, as shown before. R1 double dot gives you FR divided by M1, R hat. On the other hand, for the R2 double dot, it gives you minus FR over M2. Since we have a minus sign here, so minus minus gives you plus. Combining these two terms together, we have something like FR over mu, all right, with the multiplied to the R unit vector. Here, the mu is the reduced mass defined as in equation 9. So the whole problem becomes very simple. The center mass particle remains stationary all the time. If we take the center mass board, the center mass reference frame as our frame of reference, and we are left with one body problem whose equation motion is given in equation 8. All right, and it is the equation motion for the reduced mass particle, which is acted on by a force Fr. All right. Now, as you can see, there's no trace of the two-particle system anymore. The two-particle system has been transformed to a single-particle problem. Right? Now, this is possible because the forces involved are interacting force between the two particles. There's no external force involved at all. So under this condition, the total energy of the system is conserved, because if we make a translation from one system, one translation of the origin of the reference frame from position 1 to position 2, the Hamiltonian or the Lagrangian remains unchanged. So this invariance, according to Noether's theorem, this invariance under translation guarantees that the total energy is conserved. All right. So under this situation, the two-body problem has now been reduced to a single particle system. All right. Now, some general properties of the central force motion. If we take a closer look at equation 8, all right, R double dot, small r vector double dot equal to FR divided by mu times R hat. Now, the complete solution depends on the particular form of the force, Fr. However, a number of properties of the central force motion hold true in general, regardless of the details of the force, Fr. First of all, the motion is confined to a plane. How do we know? If we look at the, since the force is a central force along the position vector R, and can exert no torque on the reduced mass, all right? Since in the absence of a torque, the angular momentum of the reduced mass is constant, all right? L equal to R cross mu V, also equal to R cross mu dr dt. So R is always perpendicular to L by the properties of the cross product, okay? However, L is fixed in space, and it follows that the vector R can only move in a plane perpendicular to L through the origin. So without laws of generality, we can always choose our coordinate in such a way that the L points in the z direction, and the motion of the reduced mass particle is confined in the xy plane, right? So we have, to begin with, we have a two-particle problem going to the center mass frame because of the special nature of the interacting force between the two particles. We can reduce the two body problem into a single body problem, all right? Since the interacting force is acting on the reduced mass particle is a central force, so we can reduce a three-dimensional single body problem to a two-dimensional single body problem, okay? So there are only 2 degrees of freedom. Now, in the polar coordinates, the equation of motion in equation 8 becomes, that's the radial equation and also the angular equation, all right? Since there is no torque, so we have 0 here. And in the radial direction, we have a central force, Fr. Now show that the energy and angular momentum are constants of motion. Can anyone answer this question quickly? Since it is a central force, so the Hamiltonian of the reduced mass particle will not be changed under rotation, right, about the z-axis or any axis. By Nernst theorem, the angular momentum must be conserved. Am I correct? Okay. So you don't have to do any calculations, and you get the full marks. However, if you don't know this, if you haven't learned about the Nernst theorem, then you have to work it out, right? Now, how about the energy? We just discussed this, because the Hamiltonian or the equation motion is invariant under translation. So by Nernst theorem, the total energy must be conserved. Okay. Now, exercise 2, you have to do a little bit calculations. Prove the law of equal areas. Prove the law of equal areas. I think you have done this in those STOT classes, right? You have done this exercise in the STOT classes before. STOT. Those special problem classes. Am I right? The stop. Okay. All right. All right. So the law of equal areas states that for any central force, R strips out equal areas in equal times. This is the consequence. This is a derived consequence of the conservation of angular momentum. Okay, so if you can start with the conservation of momentum, angular momentum, and derive this. Okay. Now we try to look at try to derive the Lagrangian of the reduced mass particle of the two body problem. All right. Our kinetic energy 1/2 m1 r1 vector dot square plus 1/2 m2 r2 dot square. All right. And then we make a change of variables. We express these two terms in terms of the center mass coordinate and also the relative coordinates. All right. And after simplification, we can see that the kinetic energy consists of two terms. The first term, the kinetic energy of the total mass. Okay, the center mass, the center mass particle. And another term is the kinetic energy of the reduced mass particle. Right. If we choose the center mass frame as our reference frame, then the first term will disappear, will vanish automatically. Because in the center mass frame, the center mass particle will not move. All right. And how about the potential energy? Very simple. This is the potential energy is equal to can be obtained by this relation, because the force, central force Fr, R hat, is derived from this expression minus du r dr, right? The Lagrangian, L equal to T minus V. So this is the Lagrangian of the system. Again, as I pointed out before, if we choose the center mass frame as our reference frame, then the first term disappears. We are left with the kinetic energy of the reduced mass particle and also the potential energy. All right. Now we can easily see that the Cartesian coordinates x, y, z of the center mass coordinate are cyclic coordinates. So the corresponding linear momentum must be conserved, right? Because these are cyclic coordinates. So the px is constant, py is constant, pz is constant. All right, and the momentum itself must be conserved. In other words, dp vector dt equal to 0. Okay. Now, since the system of the reduced mass has spherical symmetry, the angular momentum is conserved in accordance with the Nernst theorem. In addition, as L is always parallel to the normal vector of the plane spanned by R vector and P vector, right? Because L is equal to R vector cross P vector. Okay, so the motion of the reduced mass must be confined to a plane perpendicular to the L vector. Okay, and as I mentioned before, we can always choose the angular momentum axis to be the z axis, and the particle and the plane in which the reduced mass particle is moving is the xy plane, right? Now, if we take a closer look at equation 19, which defines the Lagrangian of the system, or the Lagrangian of the reduced mass particle, we can see that theta, the angular coordinate theta, is a cyclic coordinate, all right? So the corresponding generalized momentum must be constant, must be conserved, all right? P theta, which is actually the angular momentum, must be conserved. Besides, the Hamiltonian is also conserved, right? Now, the Hamiltonian can also be expressed in terms of the angular momentum, L, in this form, okay? So, the first term is the kinetic energy in the radial direction, and the second term is the centrifugal potential barrier, all right? We call it centrifugal barrier. And the third term is the potential energy term. Combining these two, we call it effective potential for the reduced mass particle. All right. Let us, since E is a constant, L is a constant, so let us re-express this equation in the form of equation 23. Now we can see the R dot is equal to plus or minus square root of this quantity, all right? So we can express R dot in terms of the E and L. Now, solving this equation will give us the solution, which express R as a function of t. Okay. Now, in general, this is difficult to solve. All right. In general, this is difficult to solve because of the function UR. Right. Now, once the UR is known, we can solve the equation, this equation motion, either analytically or numerically. Unfortunately, we only have a very small number of cases that can be solved analytically. Okay. So in other words, in most cases, analytical solutions are not available. And we have to appeal to numerical calculations. Now, instead of expressing the solution as a function of t, R as a function of t, we can also express the solution in terms of R as a function of theta. All right. So this is the trajectory. So d theta dr equal to d theta dt times dt dr. All right. So what is d theta dt? What is d theta dt? We go back to the angular momentum here, equation 20. Theta dot mu r squared theta dot equal to the constant L. So theta dot is equal to L divided by mu r squared, right? So we can rewrite this expression, okay, R as a function of t as theta, R as a function of theta, all right? So we substitute d theta dt into the expression, and after simplification, we realize that d theta dr is given by this. Now, if we can solve this equation, this is a first order differential equation. It can be done easily, right? However, if the UR is a power law potential, if UR is proportional to R to the power n, there are only 3 cases which have analytical solutions or closed form solutions. All right. Besides these 3 cases, no analytical solution can be obtained. Can you show it? Only these 3 cases, only for these 3 cases, equation 25 can be solved analytically. Is it true? Is it true? Is it true? Now, to check it is very straightforward. We move this dr to the right-hand side. Okay, move the dr to the right-hand side of equation 25. We know that L is a constant, E is a constant, all right? Mu is a constant, and UR is proportional to Rn. If we can integrate this integral, then we are all set. Okay? So let us have a test on integrations. All right, I give you 10 minutes to work on it. According to the statement, the integral can be evaluated analytically if n equal to 2, minus 1, and minus 2. Is it true? Is it true? Okay, 10 minutes for you to work it out. L is angle dimension. For A equal to minus 2, we have 2 naught over R squared minus L squared over 2 mu R squared. Okay. Now, we move this R squared inside the radical sign. What will be there? We have R squared, 1 over R is here, 1 over R squared is here, all right? And we know that for the A of R squared is it really true? We have R here. Okay, this is for n equal to 2 minus 2. How about for n equal to 2? For n equal to 2. This is for n equal to minus 2. So for n equal to minus 1, okay, okay, if I multiply R1 R inside, we have R squared, R, and here, right? Hey, can you try this? Here. So you can sit here.
Thank you.
Cái gì để đeo tay notebook或者係 iPad， 咁而家問題就係，我哋列晒咁多機就呢個 A 而家，咁2變黃要墮落啦，係咪？咁我嚟咧，我本身就話，我話咁多個 mathematics 我睇下佢識唔識編俾你睇嘅喎，有可能係。So we have one out outside. Okay.
Oh, we don't need to really because it's turned into a root
好肯定一樣嘢咧，就 A 等於1應該係10嘅，點解啊？因為 square 我話好多，所以係一個都係我哋知道一定可以做嘅。Yes. A 呢個條 Q 咧就係個 harmonic oscillator。如果都係揾唔到 mathematical 咧，咁我哋去翻啲老人家嗰度啦，又要做乜嘢啊 ？Tables of integrals 啦，係嘛？譬如你將來你可能做 research 咁樣，你遇到一啲 integral， 你搞好耐都揾唔到嗰個 trick， 咁你要點做啊 ？Tables of integrals 啦，咁咧有一本書咧，專 calculate 晒所有嘅 tables of integrals 㗎啦。咁係一班東歐人啦，定係俄羅斯人寫咗出嚟，好似本厚以前嘅電話簿咁厚嘅。如果你喺好多時候咧，你未必直接攞到個答案嘅，但係咧，當你去 look up related 嘅 integrals 嘅時候咧，就會俾啲靈感你嘅。咁誒做一個 suitable substitution 啊，咁你又可以做咗好多嘢，可以完成咗佢啦。咁喺嗰本書裏邊，基本上你如果都揾唔到嘅話咧，你都可以放棄啦，即係話冇乜機會可以得㗎啦咁樣。 Good. Conic section 有冇印象啊？因為你 integrate 咗就係個 R 係十分 function theta 啊嘛，咁咪應該係個 conic section 嘅 equation 咯，係咪 ？OK， 所以應該係做到噶嘛。啊 ，OK，anyway， 好啦，不如咁樣啦。呢個既然咁有趣，咁就嚟緊呢個功課就係呢個其中一題啦。係咪？我都講咗，如果你唔識做，應該係有幾個方法啦 ，Mathematica 啦 ，Tables of Integrals 啦，係咪？咁你當然你要明白到點出嚟啦，唔好就咁抄個答案啦。Okay, so now we have the Lagrangian. Okay, we can derive the Euler-Lagrange equation. And we only have the Euler-Lagrange equation motion in the radial direction because the angular direction just gives you the angular momentum being conserved. Here in the radial direction, we have this equation of motion, mu r double dot minus r theta dot square equal to the central force. Okay. Now, it is very common to make a change of this change of variable, u equal to 1 over r. Okay, it is very common to do this in substitution. By this substitution, we can rewrite this equation of motion in equation 26 as follows. First of all, we write du d theta. Okay. R is a function of theta. So we apply the chain rule. We have du d theta equal to minus 1 over r squared dr d theta. And dr d theta is equal to dr dt dt d theta. All right. Now d theta, the theta dot is simple. It can be obtained from the angular momentum expression. All right. So we get this. So after simplification, we realize that the du d theta is equal to minus mu divided by L times R dot. The second derivative can also be obtained easily by the chain rule. And this equation gives us, it relates, the second derivative of u with respect to theta is equal to minus mu over L, R double dot over theta dot, all right? And we can replace this, express this theta dot in, replace this theta dot as the angular momentum. So the final expression is equal, the final expression is minus mu square over L square times R square, R double dot, all right? So we obtain the first derivative of u with respect to theta, and also the second derivative. Okay, so R theta dot square is equal to R times L over mu R square, close bracket square, and it is equal to this, okay? Then we substitute equation 28, 29 into 26 into this expression. What do we get? Okay, we get a very nice expression. Very nice expression. The second derivative of u with respect to theta plus u equal to minus mu over L square times 1 over u square times the force, okay, the central force. Okay. Now we express everything in we go back to R again. This equation 30 is equal to this. All right. Okay. Now equation 31 can be used to find the force law that corresponds to a known orbit. So if we, by observation, we know the orbit of a particle, a reduced mass particle, then we can determine the force governing the motion of the particle. Okay, so in other words, we reverse the problem. To begin with, we give you the force, a central force. Okay, and then solving the equation of motion, we can determine the trajectory of the particle, of the reduced mass particle. Right? Given the force or given the potential energy, we can determine the particle's trajectory. Now we reverse the process by making a lot of observations. We know the trajectory very, very clearly. Then we can deduce the force acting on the particle, all right? By using this equation 31. Can you follow me? Motion 啦，或者係個關係 equation motion， 咁就 solve 咗之後，無論你係可以 analytical 去solve 咗佢，或者係 numerical 嚟 solve 佢，你就會有個 particle 嘅 trajectory 嗰個 orbit 就會出現㗎啦。OK，numerical solve 你都可以畫佢出嚟㗎嘛，咁咪唔知咯。OK， 嗱，另外一個問題就話，好似 Tesla 咁樣，我不停咁樣。我手頭上攞到好多 data， 就係關於每時每刻佢嗰個 orbit 佢有個 position 咁我跟住問嘅就係點解佢會咁樣行法嘅咧？咁梗係有個 force acting on 呢個 particle 啦。咁個 force 係點嘅樣㗎？咁我哋去現實去做啊，就諗得出嚟啦。OK， 得啦。 你可能都係 analytical 都得㗎。譬如我而家呢個俾個 example 你。如果我話嗰個 orbit 咧係一個 circle 嚟嘅，咁個 force 會係點㗎？你係個 circle 嗰個 r 嗰個 constant 啦，你 differentiate 佢又係零啦，一 over r 又有 constant 啦，咁自然 according to equation 31，咁個 force 係點啊？一定係1 over r square 啦。OK， 咁但係如果你發覺到你嗰個 orbit 唔係咁簡單嘅時候，會點咧？例如第二個 example， 如果 orbit 係 r is an exponential function of theta， 咁個點算啊？Get a very nice result, which is equal to alpha square divided by r。哇！真係估都估唔到，咁好彩嘅，係嘛？咁啊，梗係做馬㗎啦呢個，唔做馬邊會有咁好彩啊？咁啊 ，based on equation 31就係點啊？加翻個1 over r 係咪？加翻個1 over r。咁本身佢已經係 alpha square over r， 再加翻係1 over r， 咁就係 alpha square plus 1 over r 嘅啫。OK， 咁用翻嗰條 formula equation 31，咁啊簡單個食菜啦。咁啊 alpha square plus 1 minus 1 over r， 咁啊將呢個 r square 調翻過嚟，咁你已經揾到個 fr 啦。OK， 咁呢個 fr 就好奇怪嘅，就同3係 inversely proportional to r cube。OK， inversely proportional to r cube。咁到底嗰個 trajectory OK，so 如果而家跟住問啦，如果個唔好彩你冇一個 form 出現，咁點算啊？你即係有 numerical 嘅 result 出現，有晒 data 啦咁樣，咁點算咧？你會點做啊？你得條 equation 嘅啫喎，咁嗱，再嚟咯喎，我有 r as a function of theta 嘅 data， 嗱記住 data 唔係一個 function 啊，係有晒呢啲 data， 我哋 plot r versus theta，OK， 我哋知道啦，咁我點樣去定個 fr 出嚟咧？OK， 變咗個 finite difference。OK， 你將佢變成個 finite difference for 個 second derivative。咁但係咧，咁嘅意思即係話你啲 data points 要點樣啊？夠密，係咪？夠晒密啦。OK， 夠晒密啦。All right， 所以嗱，咁所以你要記住咯，如果你要有咗個 data， 有晒個 orbit， 你想揾到底個 force acting on the particle 係乜嘢，係點嘅樣咧？咁啊用 equation 31咯。如果你知道咗個 force， 你跟住問個 trajectory 係點㗎？你要做乜嘢啊？你又要 solve， 就要解決呢一個啦。OK，equation 25啦。OK， 想揾個 orbit， 咁你要做個 integral 啦。OK， 無論你 numerical 又好 ，analytical 又好，就係咁嘅答案出嚟。All right， 所以兩 type of questions 得唔得 Okay. Okay, let us take 5 minutes break and then we continue to next topic. All right, the Hamiltonian of a central force motion is conserved, and it is given by equation 1. Now we combine the second term, which is related to the angular momentum and also the potential energy, and we call it the effective potential of the model of the system. And the force associated with it is equal to minus the gradient of the minus of the gradient of this combined potential. All right. And the second term, we sometimes give it a name called centrifugal potential energy. And the corresponding force is equal to, is sometimes called the centrifugal force. Okay. Now, if we have two non-interacting particles and move toward each other with velocities v1 and v2, their paths are offset by distance b. Let us investigate the equivalent one-body description of the particle. So the relative velocity is equal to v naught. Since v1 and v2 are constant, so v naught is also constant too. And the total energy is equal to 1/2 mu r dot square plus the centrifugal potential energy, right? And since the total energy is conserved, so the energy is also equal to 1/2 mu v naught square, right? So they are when they are far away from each other. When M1 and M2 pass each other, the shortest distance is equal to B, and R dot is equal to 0, the relative velocity. Hence, this term, L square over 2 mu B square is equal to 1/2 mu V naught square, all right? Then the angular momentum of the system is equal to mu B V naught. As the particles approach, the kinetic energy decreases, vanishing at the turning point, where the radial velocity is 0 and the motion is purely tangential, right? Because they just the reduced mass particle just perform simply the angular motion. Once the turning point is passed, R increases and the particles separate. In our one-dimensional picture, the particle bounces off the barrier, all right? So if we look at this figure, that means the particle comes in, okay, reduced mass particle comes in, and when it hit the closest distance, it will go back again, bounce off again, all right, and flies away. Now we have an inverse square law for the interacting force. Fr is equal to minus k over r squared. So the potential energy is equal to minus k over r. And the effective potential energy is equal to minus k over r plus L squared over 2 mu r squared, all right? So this is the effective potential energy for the inverse square law case. And the combined potential energy is given by this solid line. Okay, this solid line. So if the particle has energy E1, the particle has energy E1, what will happen? It will come from afar. When it hit the When it reach R1, it will bounce off again, go back, all right, and flies away. So this motion is unbounded. For the case E1 equal to 0, E1 equal to 0 energy, what happens? It will come in and hit the potential barrier, okay, and bounce back. So this is a watershed between bounded motion and unbounded motion, all right? When the particle has energy E2, which is negative, what will happen? This motion is bounded between R2 and R4. That means the particle start moving in from R4. When it hits R2, it will bounce back again, bounce off again, and try to move towards R4, okay? So it is going back and forth between these 2 points. Now finally, if the particle has energy E3, what will happen? It will stay at the position R3 indefinitely, okay? Now, what does it mean? That means the orbit is circular. What? Oh. Does it work now? Can you see it? Okay, all right. So let me quickly summarize it again. When the energy is E1, it is unbounded motion. It comes from afar and hit the boundary, hit the potential barrier, effective potential barrier, and bounce off and flies away. When E1 is equal to 0, this is the borderline between bounded motion and unbounded motion, all right? When the energy is equal to E2, the particle is bounded between these 2 points, R2 and R4. The motion is just back and forth motion. When the energy is E3, the particle will be staying at R3 all the time. And that means the orbit is circular, all right? There is one other possibility, i.e. L equal to 0. What will happen if L equal to 0? The UC equal to 0, then we only have the minus K over R, okay? We have minus K over R. So the particles move along a straight line on a collision course, because when L equal to 0, the centrifugal barrier cannot hold them apart. So they will have a head-on collision, okay? Now I changed the question a little bit. If we look at a special case of an isotropic harmonic potential, what will happen? That means the potential energy is proportional to R squared. What will happen? R squared, proportional to R squared. Then it is obvious that the particle motion is always bounded, right? Always bounded, because As r goes to infinity, the potential goes to infinity as well. So the motion is always bounded, all right? Again, at the minimum potential point, at the minimum of the potential of the effective potential, the orbit is circular, right? Because the particle is confined at the position R3 again. Okay, so we try to figure out the orbit for the inverse square law. So what we need to do is to evaluate this integral, as pointed out in our last lecture notes. We need to integrate this for the case n equal to -1, n equal to -1. Now, how do we do it? First of all, make a substitution, make a change of variable. Instead of integrating over r, we will express the integral in terms of u, which is equal to 1 over r, u equal to 1 over r, all right? Now, if we do that, the integral can be simplified a lot, as you can see in the equation 12. Now, the integral is equal to, the integrand is equal to 1 over square root of this term, all right? Okay? Then we can further transform this integral in equation 12 as this, all right? So basically, we make a completing square, we perform completing square, all right? And we move out, we factor out this factor, okay? We factor out this factor, we call it epsilon squared, all right? Then the integral becomes this. Do you know how to solve this, perform this integral? Trigonometric functions, right? Okay. So we let f, another substitution, we let f equal to alpha u minus 1 over epsilon. Then the integral really becomes very simple. It is equal to this, all right? Then we realize that this is the arc cosine function, okay, arc cosine function. All right, so equation 15 tells us that tells us the orbit of the particle alpha over r equal to 1 plus epsilon cosine theta plus beta, right? And this is the equation for a conic section of eccentricity epsilon and the lattice rectum of the orbit equal to 2 alpha. Okay. Now, the minimum value of r is called the pericenter. The maximum value of the radius is epicenter. The turning points are abscissa. The corresponding terms for motion about the sun are perihelion and aphelion. And for motion about the earth, we call it perigee and apogee, all right? For epsilon greater than 1 or capital E, that energy greater than 0, we have hyperbola. The epsilon equal to 1, energy equal to 0, we have parabola. Epsilon lying between 0 and 1, we have ellipse. Epsilon equal to 0, we have circle, all right? Now, if instead of having the inverse square law, or n equal to -1 for the potential energy, what kind of trajectories do we expect for the case of harmonic oscillator? What kind of orbit do we expect for the case of simple harmonic oscillator? It means the potential energy is proportional to R squared, okay? So the energy, potential energy is proportional to R squared. What will happen? Okay? Without going through the calculations, what do you think? If this U is replaced by a curve or a function proportional to R squared, what will happen? What kind of orbit do you expect to have? Yep. So the potential will look like this. This is the total potential, the effective potential. So what kind of, if you have energy equal to that, what is the trajectory? She said bounding ellipse. I can tell you this answer right away. If it has an energy touching the minimum of the potential, it must be a circular orbit. Okay? If it is, I call it E naught, if this E1 greater than E naught, what is the orbit? It is a bounded motion, right? What is the orbit? Okay, for the case of simple harmonic oscillator, isotropic simple harmonic oscillator. Yeah, at this point, I can certainly say that it is a bounded orbit. Right? And also, it is a closed orbit. When you go back to the original system. But do you know exactly the shape of the orbit? Okay. Chúng tôi đang bắt nhớ đó. Chúng ta bắt nhớ đó. Không thế nào? Đi đầu tiên số của họ. Ở những cái đó. I can do exercise. Không do exercise. Chúng nó. Bởi vì là em là chủ giác, nó là chủ em là chủ giác, có thể bắt đầu. Với chủ là không tách. Còn em là chủ giác, ở bất giác. Thì mình chi về hả? Mình chi rồi, chi về đấy. Còn chi đầu tiên thì cái họ không tách. Tại nhớ đi vào là gì? Tại cái điện chắc là không được chi rồi. Nếu mà có áo thì nó làm gì vậy? Đấy, nó làm gì vậy? Nó mất về ô. 啦，睇下會叫做咯。咁但係其他嘅單嘅波係點咧？你睇咗就知啦。咁啊，抄嚟嘅咁啊，咁 n 等於負二咧 ，n 等於負二咧點算啊？n 等於負二，咁啊好似嘅 n 等於負一嘅喎，其實好似 n 等於負一嘅 ，n 等於負二，都係咁樣，仲就係 oppose to zero， 係嘛？OK， 咁我哋又知道嘅最低嘅如果有個 minimum 嘅話，咁呢個 minimum 嗰咧應該係最，但係其他嗰啲唔知嘅，係咪？未知嘅。好啦，咁喺個功課嗰度去慢慢分曉啦。OK，up till now 有冇咩問題？OK。嗱，喺呢個 case 就冇用啦。如果食嘅，即係問個同學問嘅，如果喺 exactly 嗰條嘅時候，到底係 bounded 啦定係唔 bounded？好明顯係 zero plus 咧，我就知道 unbound 㗎啦。zero minus 咧，我就知道 bound，得唔得？明我講嘛 ？zero minus 同 zero plus 我就知㗎。咁 zero 係點㗎？zero 係點㗎？exact zero 就係個問題，係咪？再講就，我哋好肯定睇得出圖 E1 係 zero plus 係 bounded motion 啦，定係 unbounded motion？unbounded 係嘛？無論幾弱，佢都有能量㗎嘛，佢都唔喐嘅係咪？佢由好遠咁樣走嚟，好遠嘅時候即係咩啊？佢有finite energy，無論幾細，佢都有 energy， 係嘛？好似佢龜咁慢，佢都識行，係嘛？如果係 E2 E2 係個 zero minus， 佢就係單獨嘅咯喎，係咪？無論係幾細，幾叻幾即係多叻嘅方，佢就係單獨嘅。即係話咧，佢走咗過嚟，即係你不放 E2， 拗到好近，好近拗好長㗎，已經係。咁但係咧，佢離開咗之後咧，佢一路，但係未去到 infinity 咧，佢就會點㗎？單 step 㗎，嗰條拗波嘅單 step。雖然拗波好大，但係佢真係快嘅，係嘛？但係零咧點算啊？銀班嘅有啲人認為係銀班嘅，有啲人認為係班㗎。零 exactly 等於零 exactly 等於零 ，OK？銀班，喂，再嚟個啦，個 total energy 係零 ，OK？total energy 係零，到底係銀班啊定班啊？銀班唔班啊？ 我哋正話答得好爽嘅，超級銀包，超米包，即係我哋識嗰啲名就銀包。然後下低呢識嗰啲名嘅話咧，都係叫包。但係食嘅嗰邊咧，點算咧？食嘅嗰邊話呢等嘢。係啊，OK 啊，睇翻正話嗰個啦，係咪？OK 嗱，咁咧就你嘅同學就話，我哋翻嚟啲 equation 嗰度睇睇啦，呢等嘅人啦，係咪？咁你會得到乜嘢咧？UR 咧就係one over 嘅嚟嘅，one over 係咪？咁佢係點嘅咧？你見到乜嘢 orbit 咧？你會見到乜嘢啊？班定唔問班？cotangent，OK，咁同 cotangent 點㗎？嗯哼，嗯，咁係啦，呢個其實翻返去嗰個咧就係嗱，如果 energy 等於E 等於零嘅呢個就係一啦，係咪？呢個係一啦，咁剩翻嚟就依然係呢嚿嘢嚟嘅喎，係咪？呢個一依然係呢嚿嘢，咁你得咗乜嘢啊？E 等於零，OK？E 等於零，個 epsilon 等於幾多啊？一 epsilon 等於一係咩啊？parabola，所以係 unbound 嘅，係咪？係咪啊？ 所以你係講啱咗，翻返嚟呢度睇下啦，咁樣咁咪睇翻啦。OK，好啦，咁我哋今日係咁先，星期四繼續，咁就功課應該今日晏晝或者 evening 應該準備好噶啦。咁你哋多啲時間去玩下呢個 integral 啦。All right。